In this first part of Chapter 10, Section 10.2, we're going to begin by learning how to simplify radical expressions. A radical expression is just a math expression that has letters, numbers, and a radical sign. You're most familiar with a square root, but we have talked about things like cube roots, fourth roots, and so on. In this chapter, we're really just going to focus on square roots. But just to refresh your memory, here in the middle, you can see a radical expression. Remember that A represents the index. That tells you whether you're looking at a square root, cube root, fourth root. If there is no index, it's assumed to be a 2, and you're taking a square root. The radical symbol is here, and everything underneath of the radical sign is called the radicand. When we simplify square roots, we're going to be using perfect squares. Perfect squares are numbers, or they can be variables, that have whole number square roots. So you're probably familiar with different perfect squares. For example, the number 25 is a perfect square. And that's because if I take the square root of 25, I get 5, a whole number, no decimals or fractions. The square root of 25 is 5 because 5 times 5 equals 25. You should memorize the list of the first set of perfect square numbers. You're going to want to know numbers like 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and so on. That list of the first set of perfect squares, square root of 1 is of course 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4, and so on. So these perfect squares go in order. We also have perfect squares with variables. So let's consider something like x squared. If I take the square root of x squared, remember squaring and square rooting undo each other, and we know that the square root of x squared is just x. Well, that's because x times x gets us back to x squared. The square root of something like x to the 6th power is x to the 3rd power. That's because x to the 3rd times x to the 3rd, if you remember from a previous chapter, when you multiply letters, you add their exponents. So x to the 3rd times x to the 3rd gives us x to the 6th power. The rule for variables is that a variable is a perfect square as long as its exponent is an even number. If the exponent is an even number, and you do have a perfect square, to figure out the square root, you divide that exponent by 2. So if I took the square root of x to the 10th power, to find its square root, I take 10 and divide it by 2 to get 5. Since 10 divided by 2 is 5, the square root of x to the 10th power is x to the 5th power. Okay, let's try to simplify a few radicals, excuse me, that are perfect squares. So simplifying a radical, you are not allowed to have a decimal. A radical is in simplest form if the radicand does not have any other perfect square factors bigger than 1, and we'll go back to that idea in a few minutes. That really means that there are no other perfect squares that divide into the radicand. Okay, so for now, the first set of examples are all perfect squares. So the square root of 81, we should know, is 9, because 9 times 9 gives us 81. The square root of 100 is 10. In question number 3, when we look at the square root of a to the 8th power, remember variables are perfect squares as long as they have even exponents, which we have here. And to find the square root, we take that exponent, divide it by 2. So here, 8 divided by 2 is 4. And that means that the square root of a to the 8th power is a to the 4th power. We can use that same idea in question number 4. W to the 12th is a perfect square. It has an even exponent. So we take that exponent 12, divide it by 2, and get 6. So the square root of W squared is W to the 6th power. In question number 5, here we have 2 variables. We'll work with each of them separately, but they follow the same rules. So if I have a to the 6th power, I take 6 divided by 2, which is 3. So the square root of a to the 6th power is a to the 3rd power. Then for the b's, 10 divided by 2 is 5. So the square root of b to the 10th power is b to the 5th power. Question number 6. 49 is one of our perfect square numbers. The square root of 49 is 7. The square root of m to the 10th power, 10 divided by 2 is 5. So we get m to the 5th power. N to the 22nd power, 22 divided by 2 is 11. So we get n to the 11th power. Hey, that works pretty easily for numbers that are perfect squares. But typically, most numbers are not going to be perfect square numbers. So we have to learn how to break them down or simplify the radicals when we don't have a perfect square. So if you take a look at the next set of questions, it says up in the directions here to simplify a radical that has a radicand that is not a perfect square. We're going to break the radicand into 2 factors. One's going to be a perfect square, and the other is just whatever multiplies to give us the radicand. So the first step is to take a look at something like question number 7 and ask ourselves, okay, what perfect square number goes into 45? So if you think about your perfect square list, let's go back to the list. Start with the perfect squares that are smaller than 45. So I would ask myself, does 36 go into 45? No, it does not. Does 25 go into 45? No. Does 16 divide evenly into 45? No. Does 9 divide evenly into 45? Yes. So I found a perfect square number that goes into 45. So I'm going to take the square root of 45 and rewrite it as the square root of 9 times the square root of 5. 9 times 5 is 45. 9 is a perfect square number. Now I can take the square root of 9. We know the square root of 9 is 3. If I were to take the square root of 5, I would get a decimal. And when we simplify radicals, we're not allowed to get a decimal. So I'm just going to leave the square root of 5 next to it. My answer here is 3 root 5. Okay, let's try that again for question number 12. Number 8. The square root of 12, so 12 is not a perfect square, so I'm going to try to break it down into a perfect square times a number. So in my list of perfect squares, I could try 9, does not divide evenly into 12. Then the next one I would try is 4. 4 does go into 12. So I'm going to rewrite the square root of 12 as the square root of 4 times the square root of 3. The square root of 4 is 2. So I can take the square root and get a plain old 2, comes out of the radical. The square root of 3 would give me a decimal. I'm not allowed to have decimals, so I leave the 3 under the radical. I know this is completely simplified because there is no other perfect square that goes into 3, that goes into the radicand. So this is my final answer. For question number 9, to break down the square root of 50, again, we find a perfect square that divides into 50. That perfect square is 25. So I rewrite the square root of 50 as the square root of 25 times the square root of 2. The square root of 25 is 5. So 5 comes out of the radical. The square root of 2 stays as it is because I would get a decimal if I tried to square root 2. And this is my final answer because there are no other perfect square numbers that divide into 2. Okay, for the next set of questions, we're dealing with variables that are not perfect squares. Remember, a variable is only a perfect square if it has an even exponent. And in something like question number 10, y to the 5th does not have an even exponent. So what do we do in that case? Well, we're going to break up y to the 5th into the parts that are perfect squares and the parts that are not perfect squares. So y to the 5th is really y times y times y times y times y. The idea of taking a square root is finding a pair of items that multiply to give you the radicand. Well, if I look underneath of the square root symbol, there are 2 pairs of y's. A pair comes out of the radical symbol. So a pair of y's for the first circle and a pair of y's for the second circle come out of the radicand and represent the pairs as y to the second power. The last y that's by itself, not part of a pair, stays underneath of the radical sign. Another way to think about this that's sort of silly but often works for students is to say couples get to go out on a date. Husband, wives, boyfriend, girlfriend get to go out on a date. So they leave the house as a couple. Single people stay at home under the house. So if I have 5 people, there are 2 couples. Those couples come out of the radical as y to the second power. And the 5th wheel stays at home all by himself underneath of the radical symbol. Okay, this is our solution. There's also another way to think about taking the square root of variables. So that's to go back to the whole idea of dividing by 2. So if a variable has an even exponent, we were dividing the exponent by 2 to find its square root. We can still do that with odd exponents. If in number 11, I took the exponent 9 and I divided it by 2. 9 is not divisible by 2, but 2 does go into 9 4 times with a remainder of 1. Remember back to your elementary school dividing days. So 9 divided by 2 is 4, remainder 1. That means that there are 4 couples, 4 pairs of e's, and then 1 left over. So to write this as our answer, the square root of 9 is e to the 4th power, and that remainder, that leftover e, stays underneath of the radical. Let's try that again with question number 12. So in question number 12, m is to the 25th power. If I take 25 and I divide it by 2, 2 goes into 25 evenly 12 times with 1 left over, remainder 1. That means that within 25, there are 12 couples and 1 single left over. So to write that for our radical, we have m to the 12th power to represent the 12 couples that go out, and then the square root of m to represent that last single person staying at home by themselves. In questions 13 and 14, we're going to combine together our numbers and our variables to take the square root of something that is not a perfect square. So let's take a look at number 13 first, and let's deal with just the number portion. So if I start with thinking about just the square root of 75, I have to find a perfect square number that divides into 75. So 75 can be broken into 25 and 3. So I rewrite 75 as the square root of 25 and the square root of 3. 25 is a perfect square. When I take its square root, I get 5. 3 is not a perfect square number, so it stays under the radical. For the number part, we're finished, but we also now have to deal with the letters. So first we have x to the 7th power. So let's use our trick of dividing by 2. 7 divided by 2 is 3, remainder 1. So that means x to the 3rd power comes out of the radical, and that leftover x stays underneath. Then finally we'll deal with the y's. Y is raised to the 5th power, so 5 divided by 2 is 2, remainder 1. So y squared comes out of the radical, and that remainder of 1, the leftover y, stays underneath of the square root. This is our final answer. And for our last example, let's follow the same idea. Start just with your number. So we think of a perfect square that goes into 32. It's easiest to work with the biggest perfect square. So 4 is a perfect square number. It divides into 32. But 16 is a bigger perfect square number that divides into 32. So I'm going to break this down into the square root of 16 and the square root of 2. The square root of 16 is 4, so 4 comes out of the radical. 2 is not a perfect square. It stays underneath of the radical. Then I can deal with the letters. A to the 7th power, so I take the exponent, divide it by 2. 7 divided by 2 is 3, remainder 1. So a to the 3rd power comes out of the radical. The remainder 1, that leftover a, stays underneath. For the b's, b to the 4th power is a perfect square. If I take the exponent of 4, divide it by 2, I get 2. So I have b to the 2nd power, no leftovers. So this is going to be my final answer. Okay, tonight's homework are these last set of questions here. Please read the directions. It says do them on a separate piece of paper. Make sure you take a picture of your work, upload it to Teams under this assignment. You do need to show your work for these questions. If you have any problems or concerns, please reach out.